In Fet Amplifier, we need to talk first on biasing, secondly on Fet model, third on Fet Amplifier circuit, fourth on Fet Amplifier analysis. In this analysis, we will be seeing three things: mid frequency, low frequency, high frequency. So these are the topics that we are going to make. This is called biasing of Fet. So first let us go to biasing of Fet. When I see biasing of a Fet, we have like this. Particularly VGS, negative, positive. Negative for JFET, positive for enhancement MOSFET. Enhancement. Negative for depletion mass in depletion mode, depletion mass in enhancement mode. As a matter of fact, VGS can be positive, or this is called input bias. For example, if you see, this is for BJT. BJT also we need positive. This is vacuum tube. Vacuum tube. So when you want to study biasing circuit, we want to study all in one. That's why we want to call this circuit as universal biasing circuit. Universal biasing circuit. For example, if you see JFET, this is the characteristics. That's why negative. If you see enhancement MOSFET, this is characteristics. VP and VT. That's why I said negative here, positive here. If you see depletion MOSFET, it has both positive and negative. Negative here, positive here. Understand? That's why I said when this is decreasing, it is called depletion mode. When it is increasing, it is called enhancement mode. So depletion mass has a depletion mode and enhancement mode. So two modes are there. That's the meaning. Now let us see the actual circuit. Then just an idea. Let's go to actual circuit. Universal biasing circuit. What does it do? Take for example XYZ. Universal biasing circuit XYZ. This is VYY, RY. This is RZ. Then call it as RX. RX2. RX1, RX2. And when you want a input circuit, we have to apply Thevenin's. What is V Thevenin's here? VYY by RX1, RX2 into RX2. Then R Thevenin's is RX1 parallel RX2. So if you draw the equivalent, you will understand this. R Thevenins, this is VYY, RY, RZ, V Thevenins. Call it as XYZ, VXZ, this is IX, this is IY. In fact, this is IY, IX plus IY. And if you apply Kirchhoff's law, KVL, we call it as input KVL, V Thevenins minus IX R Thevenins minus VXZ minus IX plus IY into RZ is equal to 0. If Rx is, what is IX actually? IX is approximately 0 in BJT, equal to 0 in Fet. Approximately 0 in BJT, equal to 0 in Fet. By that, you can neglect this drop. Then what is left over? You can neglect IX. What is left over from this? VXZ is left over as V Thevenins minus IYRZ. If this is positive or negative, this is BJT, enhancement MOSFET, DMOS in enhancement mode. This is JFET, DMOS in depletion mode, like that. And this circuit is used for all. That's why it is called, I named it as universal. The word universal means that everywhere it is valid. So one single circuit you can use for all the devices, and that is actually called self-bias circuit. Self-bias. You know why this is called self-bias? This particular resistor is used for stability, and the same resistor is used for biasing. That's why people use that itself, so self-bias. Another thing is this supply itself biasing the output as well as input. That's why it is called self-bias. Single supply we are able to use, that's why it is excellent and it's cheap. You don't need to use one battery for the output and one battery for the input. And this is the best biasing circuit that we have. That's the first topic called biasing circuit. So let us use this one. For different devices, you need different values, but the circuit is same. If this particular value is negative, it is JFET, DMOSFET. If it is positive, enhancement MOSFET. That's the main idea here. So before we go into the BJT Fet amplifier, the first thing you should know biasing circuit. From this output equation, you can calculate output current. You can calculate IY. You can calculate VXZ. You can calculate VYZ. And output voltage VYZ, output current is called Q point. Q point. Okay, that's the meaning. So let's go to the second topic called Fet amplifier circuit. The first question comes, which FET? This is valid for all FETs. Why? When you say FETs, there are two aspects. One is DC, second is AC. For DC, some devices require negative VGS. Some require positive VGS. But when it comes to AC, what happens is all will become grounded, all supplies grounded. Therefore, AC analysis is same for all FETs. AC analysis is same for all FETs. So one of the good news is you don't need to study separately. Whether it is a JFET or MOSFET or all types of FETs, AC analysis is same. For example, you give VDD negative, but once it is grounded, 0. Give positive. Once for AC, it is 0. 0 volts means ground. So whether it is N channel or P channel, whether it is JFET or MOSFET, it is grounded. That's why AC analysis is same. So when I am going to talk about an amplifier, particularly in FET, it can be any FET. It can be a JFET or a MOSFET. P type, P channel or N channel. Any type, any mode, any material. We have very interesting conclusion. Analysis is same. So then when I'll take for example FET amplifier. Though I take a JFET, but it is valid for all FETs. Though I take JFET, it's valid for all FETs. So let's take the circuit here. This is the circuit that we have. RX1, RX2. You can call it, or you can say RG, RG. Drain, RD, RS. Gate, this is N channel. Gate, drain, source. Gate resistance 1, gate resistance 2, source resistance, drain resistance. But as I said, whether it is N channel or P channel, same. JFET or MOSFET, it is same. But the question comes, how to convert a biasing circuit as amplifier circuit. This is a biasing circuit. To make it an amplifier, I need to give AC. If I am giving a source, there must be some source resistance. Every source will have a resistance inside. That's called source resistance, Vs, Rs. Then you have a capacitor here, Cb. Blocking capacitor. Blocking. What does it block? It blocks DC, allows only AC. Similarly, at the output also, we need a capacitor which allows only AC. And then we have RL and a capacitor called CL. So this is to allow only AC. And then we have a capacitor here that's called source resistance. Source capacitance. What does it do? This is having two dimensions. Open circuit for DC. When this is open, RS present. And short circuit for AC. RS is 0. So what is the purpose of this capacitor is? Open circuit for DC means stable Q point. And it's not there means zero resistance means no loss of gain. There is no loss of gain. So these are the basic how the circuit came. So these two are used for biasing. This is for stability. This is for load. This is actual also load. Then you may say, what's the difference between this load to this load? This load is, if you vary this load, Q point and A affected. But here, if you vary this, Q point is not affected. So load, Q point not affected. Like this. Whereas this load, Q point affected. So which one is better? This one is better. This is called load capacitor for the sake of bandwidth. So bandwidth variable. So in the conclusion, we are going to enjoy two ideas here. Gain is minus GM RL. You can call it as RL parallel RD. Then second conclusion at the end, I am going to give you bandwidth is 1 by 2 pi RLCL. These are the most crucial ideas about any amplifier. Be it a Fet amplifier or a BJT amplifier, any device, but all that varies is GM. As GM varies, gain varies. So gain varies with GM. That's the meaning there. GM. Now what actually I am trying to say, if you vary CL, bandwidth varies but gain is not affected. If by changing CL, bandwidth affected but not gain. That means you can vary the bandwidth without affecting gain. That means gain bandwidth product need not be constant. So when gain bandwidth product need not be constant, we call this as a very beautiful idea. The very purpose of CL is to vary bandwidth. That's why I have written there, variable bandwidth. Similarly, don't vary RD because it is AC and DC both are affected. Only vary RL, gain is affected. So by changing RL, gain is affected without Q point. So I have very interesting two conclusions. RL, what is it doing? Gain varies without Q point affected. Then what is CL? Bandwidth varies without affecting gain. That's the meaning of the second title called Fet Amplifier circuit. But if you see so many things there, so many capacitors, you have these capacitors called CB, CC, CS. They're all microfarad. And CL, internally there are three capacitors, CDS, CGS, CGD. What are they? Gate to source capacitor, drain to source capacitor, gate to drain capacitor, they're all picofarad. So all these three capacitors are internal, these capacitors are external. All these three capacitors are external and these three are internal. This is also external but pico. So some people are saying by mistake all external capacitors are micro. That's not right. External, this is here pico. So it should only say some microfarad capacitors, some picofarad capacitors. Actually, I'll give you some values here. This is 1 mega ohm, 1 kilo, 10 kilo, 4 kilo. This is 0.1 micro, 0.1 micro, 100 micro. And this one is 1000 picofarads. I'm just giving the values so that you will understand why I said it is micro and why I said it is pico. Maybe, but the very interesting thing that everybody should learn that this is 0.1, lesser, smaller value. It's not like what you call BJT. In BJT it is larger, but in fact it is smaller. That's why there is a very interesting saying, Because resistance increased, capacitance should decrease. Whereas in BJT, this resistance is only 10 kilo, that's why this was higher. When resistance increased, this should decrease because cutoff frequency is 1 by 2 pi RC. So if both are increased, this becomes 0, no? So wherever resistance increase, capacitance should decrease, or wherever resistance decrease, capacitance should increase in order to make it a small finite value. Otherwise, it becomes very, very small. So that's a very interesting thing that one has to understand and remember. In fact, CB of FET is approximately 1 by 500 times of CB of BJT. CB of FET is 1 by 500 times of CB of BJT. That's the meaning. That's why I am here telling you this has to be a smaller value in order to have good amount of this cutoff. So this is explanation about my second topic called FET amplifier circuit. So I have taken the biasing circuit, then converted that circuit into amplifier. Then I need to talk about the response. Third topic of this is frequency response. Frequency response. What is frequency response? The word is very simple. How the circuit is responding to different frequencies. That actually is like this. Frequency versus gain. And what happens is there is a response like this. This gain is called mid-frequency gain. And if you say mid-frequency gain by root 2, that is called F1, F2. This is low frequency, high frequency. In between, mid frequency. Very simple reason, the lower one is called low frequency, higher one is called high frequency, middle one is called middle frequency or mid frequency. Here microfarad is reacting, picofarad is open. In this region microfarad is short circuit, picofarad is open. In this region microfarad is short circuit, picofarad is reacting. The whole idea is here one of them is reacting. The word reactance is also a very interesting word. It reacts to what? It reacts to frequency. So this is reacting. This is also reacting. Now, because something is reacting, it is depending on frequency. Here also depending on frequency. Here, one is short circuit, other is the open circuit. Therefore, there is no response. It is purely resistive. We have resistors, but all the capacitors get us shorted and open. It's purely resistive. That's why independent of frequency. I told you what it means by micro, what it means by pico. This is how the response is going to be, but I need to tell you how this curve has become, how this curve is becoming mathematical. How do I support this mathematically? For example, AVL is equal to AVM by 1 minus J F1 by F. This is between 0 to F1. Second one, AVM is directly AVM. Third one, AVH, AVM by 1 plus J F by F2. This is F1 to F2. This is F2 to infinity. So what a beautiful idea I want to teach you. It's starting from 0 to F1, then F1 to F2, then F2 to infinity. That means you are really starting from 0 to infinity. And 0 to infinity, the whole Frequency is divided into three parts. AVL means low frequency. This is mid frequency. This is high frequency. So what you have qualitatively, you have quantitatively. That's called mathematical treatment. Every qualitative response should have a quantitative response. I will also tell you what it means. For example, why this is increasing, I need to show. Look at here. As frequency increase, 1 by increase is decrease, 1 by decrease, increase. Once again, as frequency increasing, this value is decreasing, 1 by decrease is increase. Look at here, why it's falling. As frequency increase, this will increase, 1 by increase, decrease. Understand? Therefore, you are able to see how these two equations are rising and falling. And here, independent. That's why AVM direct. Now the question comes to a student to understand, where should I start my story? Should I start from low frequency to mid and then high frequency, or where? You decide, because this is AVM, the same AVM is used here, the same AVM is used here. That means what? You need to start here. Go to mid frequency, understand AVM, come to here, calculate F1. And come to here, calculate F2. So our approach is going to be so simple. First I'll start my story with the mid frequency, then I'll go to low frequency, then I'll come to high frequency. So these are the three things. That's how we are going to go. The very purpose of the mid frequency is to calculate this. Of course, we do calculate Ri and R0. Then we will be going for low frequency in order to estimate this and in order to estimate this. That's all. We don't calculate gains here. We just calculate cutoffs because gain is already available. That's called frequency response of an amplifier. Fourth heading. That is called Fet models. For any device, there should be a model. Before you go into analysis, you should have a mathematical model. That model is developed on ID is function of VGS comma VDS. VGS comma VDS. Now for such an equation, go to Taylor series. Taylor series. That is called change in ID is equal to into VGS. Dou ID by VDS into VDS. In fact, you will also have something called half of dou square ID by dou VGS square into VGS square. Dou square IDS square by VDS square into VDS square. Like that. What am I saying here? For small signal, we are going to really talk about small signal amplifiers. For small signal amplifier means signal is small, that is voltage amplifier. For small signal amplifiers or voltage amplifiers, the change is small, neglect this. Neglect this. For example, if the change is small, square is much smaller. Then you are left with only this and this. And ID by VGS is called GM. This is called GM. And ID by VDS is called 1 by RD. Because voltage by current is resistance, but current by resistance is 1 by RD. Current by this conductance here. So if I have to say, for this is, please understand, this is DC characteristic equation. And if you now talk about for AC, what is happening is, for AC, change in DC is called AC. This becomes GM into VGS plus 1 by RD into VDS. ID is GM into VGS, 1 by RD into VDS there. 1 by RD into VDS. Now please look at this equation, you talk about it. Conductance into voltage is current, voltage by resistance is current, current is equal to current plus current, it's making a KCL or a node. Kirchhoff's current law or a node. Node means. So then how do I draw this diagram here? For example, source here. At the gate there is nothing but for the voltage. And then you have a drain here. That is GM. GM, VGS and RD. VDS and ID. VDS and ID. So this is how we have this connection. So ID is, if you write this KCL once again, current entering is equal to leaving. VDS by RD. Same thing comes. So please enjoy this. There is a DC equation. I applied Taylor series, converted into AC, you got the model. And this is model called low frequency and mid frequency because internal capacitors are open circuit. But if you really go for high frequency and radio frequency, what happens? What happens there? First you draw the same thing. Same thing there. First you draw the same thing. Then as I already said, there is an internal capacitors comes into picture. You have one capacitor here called CGS. Another capacitor here called CDS. CDS there. Or CGD. And at the end you have one capacitor called CDS. So extra capacitors are come into picture. This is of an order of picofarad and this is an order of picofarad. This is an order of picofarad. This is 10 kilo and GM is 2 milliamperes per volt. So this is called the models of FET. Which FET? All FETs, because for AC all FETs are same. Fifth topic is mid-frequency analysis. So as I told you, there is a FET and here is the circuit. RS. RG1, RG2. CS. CC, RL. CL. Output is here. Then we have RS and VS here. CB. Suppose this is 30 volts, 10 kilo, 4 kilo, 1 kilo, 1000 pico, 0.1 micro, 0.1 micro, 1 mega, 1 kilo. This is 100 micro. And as I mentioned, GM is 2 milliamperes per volt. Internal resistance is 10 kilo ohms. When you go for mid-frequency analysis, you need to draw mid-frequency equivalent. This is N channel. So we call this as AC equivalent at mid-frequency. AC equivalent at mid-frequency. What is it? When you say mid-frequency, as I already told you just now, all microfarads are short circuit. Picofarads are open circuit. Then what it means by AC? Supply is grounded. Why supply is grounded? If any constant is there, for example, VDD is 30 volts. AC means what? Change in VDD, change in 30 volts is 0. 0 means ground. So three aspects I need to consider. The first one is AC means the supply is grounded. Second one, microfarad shorted, this is shorted, this is shorted, this is shorted. And thirdly, picofarad open. Remember, by mistake, if we say it is short circuit, that's not valid because output is 0. Picofarad is open, microfarad is short. That's what happening altogether. So shall we try to draw the equivalent for this situation? Suddenly, supply comes down. Supply comes down. Because we said supply is grounded. And not only that, even this RG is also coming down. So, this coming down and this coming down, because this itself is coming down, it's just like a folding down actually. And this is short circuit. Because this is shorted, this is shorted. And you have RS here, VS here. Understand? Then this RL is there as it is. And CL, of course, open circuit. So there is a capacitor that got shorted here. There is a capacitor that got shorted here. There is a capacitor that got shorted there. So microfarad shorted, pico open. And in another resistor, don't forget, it's already there. RG2 is already there. That's called equivalent circuit. Now, when you combine these two parallelly, this combined parallelly, this is RG is RG1 parallel RG2. RL dash is RD parallel RL. RG is RG1 parallel RG2, RD parallel RL. Let's go for a simplified model. This is the final simplified model. Call RL dash, call RG. Another serious problem in FETs is this is RS, so we should call it as RSS. In BZ you have no problem. What you have to say, if you call this RS, this should be called RSS. You know why? To say signal source resistor. Signal source resistor. So this is RSS. This is VS. Call this as RI dash. Call it as RI. R0 dash. R0. V0. VI. This you should replace with model. That's why I have taught models first and then going for analysis. And how is the expressions going to come there? If you do the analysis, V0 by Vi minus Gm, small rd parallel capital RD parallel RL. That will come. In fact, this is approximately minus Gm RL. Why? This is 10 kilo, this is 10 kilo, this is 4 kilo. What do you mean by parallel combination? When you take a parallel combination of many things, the least one comes. That's why I said simply GMRL. Then what is Ri dash infinity? R dash means here. Infinity. Why infinity? If it is JFET, it is reverse bias input. If it is MOSFET, silicon dioxide layer, already infinity. If that is true, what is Ri then? Ri is, suppose you are here, what is this? RG parallel, Ri dash. RG parallel, infinity, RG. So you don't need to waste your time and again to really do that. You can just say this itself is the input impedance. And you know, according to us, it is so high. If you say this is nothing but RG1 parallel RG2, 1 mega parallel 1 mega is how much? 500 kilo. Then lastly, R0 dash is small rd. So R0 dash, small rd parallel, RL dash, which is nothing but small rd parallel, capital RD parallel, RL, which is approximately RL. That's the meaning. So for any amplifier, a person requires voltage gain, input impedance, output impedance. That's called mid-frequency analysis. After getting the mid-frequency, the next game is going to have is low frequency. And please understand, I am taking common source amplifier because this source is common for input and output. As you know, most of the time we like common source or common emitter, this for FET and this for BJT. So that's my fifth idea to talk. Mid-frequency analysis. Sixth one is low-frequency analysis. What do you mean by low frequency? Low frequency means microfarad reacts, picofarad open. Now look at your circuit which I have given in the previous. I will draw AC equivalent at low frequency. AC equivalent at low frequency. AC means, as I already said, supply is grounded. Low frequency is, I already told you. So now what happens is, you will have all microfarad capacitors comes into picture. RSCS, RL, CL is open circuit. And you have RD here, CC here. All capacitors comes into picture. RD here, RG1, RG2. All capacitors comes into picture. So please look at here. This is micro, this is micro, this is micro available. This is pico, open. This is parallel, this is parallel. And how much resistance is here? We called it as Ri dash infinity. How much resistance here? R0 dash small rd. Now make use of this. This circuit decides CB. This circuit decides CC. This circuit decides CS. Three capacitors will come. So that is called F1 due to CB 1 by 2 pi RSS plus RG into CB. F1 due to CC 1 by 2 pi RD parallel small rd plus RL into CC, because these two are in parallel, this is in series. These two are in parallel, this is in series. When I say RG, what is RG? RG1 parallel, RG2. If you look from here, these two are in series. If you look from here, these two are in series. Then what about last one? F1 CS, that is approximately 1 by 2 pi. Small rd plus capital RD parallel RL by 1 plus mu parallel RS into CS. So 1 due to CB, 1 due to CC, 1 due to CS. But if you see in the diagram, frequency response, you saw only F1 now. That means you can't have 3. Therefore, F1 is root of F1 CB square, F1 CC square, F1 CS square. And AVL is equal to AVM by root of 1 plus F by F. F1 by F whole square. Now what is that I am trying to say? Suppose if they say frequency is 100 Hz and F1 is here, AVL is here, AVM by root of 1 plus F1 by F whole square. So the overall cutoff is generated from here. So the very purpose of calculating all these 3 is to calculate F1. And after calculating this, that will estimate AVL. That's why I said do mid-frequency analysis and then go to high frequency or low frequency. This is called low frequency analysis. But don't forget, this model is what? You have to replace with the model. The last thing that we are studying is high frequency analysis. Remember the same circuit. High frequency means what? For example, if I draw AC equivalent at high frequency, AC means supply is grounded. High frequency means microfarad is short, picofarad reacts. That's what going to happen. Supply is grounded, microfarad short, picofarad reacts. How is that response there? Shorted, shorted. No capacitor here, RL dash, small RD, RI dash. This is input capacitance. We have output capacitance. Why? Picofarad capacitors are available. This is, please remember, this is internal. This is internal. Here internal is infinity. If you take this, output comes. If we take this, input comes. What happened to CB? Shorted. CC? Shorted. CS? Shorted. As I said, all microfarads shorted and picofarads only exist there. Now I have to calculate input cutoff, output cutoff. Because it's high frequency, I am calling as F2. What is input cutoff here? 1 by 2 pi RSS parallel RG into CI. This is 1 by small rd parallel capital RD parallel RL into CO. So CI is called for input capacitance, C0 is, in fact, we better say C0 plus CL, where CI is equal to CGS plus CGD into 1 plus GM RL. CO is CGS plus CGD plus This is CDS. How does this come? It just came from Miller's. If you apply Miller's theorem for CGD, it comes there. Now, having got, suppose in any problem that CL is not there, just ignore it. Suppose it says CL is not there, you said just ignore it. If CL is there, consider that. And as you know, capacitors in parallel get added. Now what is this? F2 is 1 by root of 1 by F2I square, 1 by F2O square. F2 is 1 by root of 1 by F2I square plus 1 by F2O square. And these are parallel here. Now having got F2, what is that? AVH, AVM by root of 1 by F by F2 whole square. So what is the whole purpose of this F2? This F2 you have to substitute here. That comes only when these two come. And what, suppose if they say any frequency called 100 kilohertz, you can substitute there. So from the known value of AVM, you are going to calculate AVH. So this is called 7-point study of Fet amplifier. Starting from biasing, goes to models, and then amplified circuit, frequency response, then analysis in all the three folds, mid frequency, low frequency, high frequency are done. This is a single thread to analyze Fet amplifier.